Okay, so in this final clip of Formulae for now, we're going to look at just a couple of specific examples which allow us just to look at some slightly more complicated examples and where sometimes certain rules may be given. So look at carbon reacting with oxygen. So if we're using a periodic table, we know that carbon is in group 4, which means it's going to have 4 electrons in its outer shell. And now that's going to have the ability to have either lose those 4 electrons or gain 4 electrons to get to that full octet. Either way, the number of gaining and losing is 4, and so the valency is fairly standard. 4. Oxygen, as we've seen in previous examples, is in group 6, and so is 2 electrons short. Now, this allows us to generate a formula of carbon oxide of C2O4, and we can see that those numbers are divisible by each other, and so we can undergo some simplification whereby 2 goes into 4 twice, and so we get a simplification down to C1O2. As always, we don't write the 1, and we'll simplify this off to just write CO2, obviously carbon dioxide. Now, in most examples of simple binary compounds like this, we would use the group number to evaluate the valency. But in some situations, we have a more complicated example. And in those more complicated examples, you would be told what the valency is if it goes above and beyond the rules that we're discussing now. Sulfur is one of those examples. Sulfur can exist ordinarily, you'd imagine its valency is 2 because it's in group 6, 2 electrons short of going to 8. However, in some situations, we're told that sulfur, in its reaction with oxygen, for example, has a valency of 4. Now, you'd be given this as a Roman numeral. You may also be told it has a valency of 6. Again, be given it in Roman numerals, and you'd just be told this information. If you are told this information, this supersedes any prior knowledge that we may have. So even though we think sulfur should have a valency of 2, we're being told here that in sulfur 4 oxide or in sulfur 6 oxide, it has a valency of 4 or 6 respectively. That has a rather large effect upon the resultant formula, because that's going to give us two formulae of S2O4 or likewise S2O6, both of which can be simplified. S2O4 in the same way as CO2 can be simplified to SO2, sulfur dioxide, and S2O6 can be simplified to SO3, sulfur trioxide, both of which have different reactivities and different abilities to interact with other compounds. So a relatively simple changing of the valency, whether it be sulfur 4 or sulfur 6, away from what we'd imagine it should be as sulfur 2, can have quite a marked effect on the formulae and product of those reactions. And indeed, sulfur dioxide and sulfur trioxide are completely different compounds, as you could imagine, and will interact with other products and other molecules in different ways. They are completely different species, dependent upon whether or not sulfur has a valency of 4 in its reaction with oxygen, oxygen being an example, or 6 in that case. But they give us rise to having examples of more use of formulae.